Everyone, welcome back to SAT Math question of the day. Let's get right into it. Our question of the day is here, and we'll do all the instructions later. Please do the question, pause, come back, and we will do it. Unit circle trigonometry. Okay, in the figure shown, an arc is subtended by the central angle measuring 2 pi over 3 radians. Radians, I see. So that's the arc length. 2 pi over 3 radians. What fraction of the circumference is this arc? Okay. Well, there's at least 2 or 3 ways to do this. Is probably not the cleverest way is to get the rate. Oh, well, wait. They gave you the central angle. They gave you the central angle, right? Yeah, they gave you the central angle. So, right, and the entire circumference of the arc would be. Wait, the entire circle is 2 pi, right? The whole thing is 2 pi. A central angle of a circle, the whole thing is 2 pi. So this is 2/3. 2 pi over 3 over 2 pi. So isn't it 2 pi over 3 divided by 2 pi? Like if you had a circle and this was a 1, but the whole circle was a 4, then this would be a quarter of a circle. Right, so it'd be 2 pi over 3 divided by 2 pi. So now you have to do the complex, that's so fast. But let's do this is a complex fraction. So it's 2, we're going to be neat now. 2 pi over 3 divided by 2 pi over 1 equals 2 pi over 3 times the reciprocal of this, which is 1 over 2 pi. 2 pi's cancel, and you get 1/3. Yeah, so calculating the radius.
Okay, so this is an example of a situation when when you understand the big picture, all of the components put together, intuitively understood in one shot. It's obvious that's 1/3.
Right. Yes.
And then you could verify that's one. You could a step to see it's 1/3 is that if you multiply what's given, 2 pi over 3 times 3, you get 2 pi. 2 pi is the angle around the whole circle.
Exactly.
And so 2 pi over 3 is 1/3 the angle around the whole circle.
Yep.
Now, in a circle, the circumference subtended by an angle is proportional. The length of the circumference is proportional to the amount of angle. Right? The amount of angle times 2 pi equals the amount of circumference.
Right.
So, the big picture is that the angle measure and the circumference subtended by the angle measure are proportional. So 1/3 of one is 1/3 of the other, or 3 times one figure is 3 times the other, right? Now, when you the logic that could be done, that's the logic that's done without the human intuition is what Joel did. You compute, okay, they're interested in the circumference of this arc. So what Joel did was say the circumference of this arc. Okay, what fraction of this, no, that's the wrong question. What fraction of the circumference is this arc? So the question is what fraction of the circumference is this arc? Well, the whole circumference is the length of the whole circumference is 2 pi divided by r.
No, no, no. The whole circumference is 2 pi times r.
Yeah, no, yeah, I said, okay, so I meant two times 2 pi.
Times.
Yeah, the circumference of the whole circle is 2 pi r.
Right.
The circumference of the part, the circumference of this arc, the circumference of this arc, the circumference of this arc is what's given here times r.
That's right. I have it at the bottom.
Okay,
See,
and then you take the ratio, and then it looks really, really ugly. But in life, beautiful, holistic, intuitive ideas, the glory of the universe, looks ugly when you look at it in the nitty-gritty details. Okay?
Right.
So what's cool is when you do and you actually like and think about math all the time, like some of us do.
Speak for yourself.
Yeah, you take the pleasure of seeing the whole thing. Often without the nitty gritty, ugly details that happen when you grind it up, but without a human intuitive picture.
Yep. So
Okay?
this is just
so approach to the SAT is that when you could understand the situation of a problem intuitively, go for it.
Yeah.
The answer is a third.
Right.
That's the end. And then move on to the next question.
Right. Now what we did in order to do the thing that's in the red box, which is now I'm circling in blue, you need to know that the arc length of a circle is the central angle theta times the radius. Arc length, which is sometimes called S, is r theta. Now
the arc length of a what's the portion of the circumference?
A second.
Of an arc. The arc length of an arc.
Yeah. So let's just take a quick look and see if that's on the reference sheet that you're given on the SAT. Oops.
Okay. What is wait, put in your S. S is
the arc length.
S is the length of the arc.
Traditionally use the letter S for arc length. Arc length is r theta, r radius times the central angle. Now I'm afraid we're going to have to actually we'll clear the annotation. Because we need to see what is given to you on the SAT in terms of reference sheets. It is not given to you the formula that the
no, they're not giving
they do not give it to you, but they suggest it. They suggest it on the first one here, where they say the circumference is 2 pi r.
Yeah,
that's because the whole and by the way they say here the number of radians in arc is 2 pi.
They remind you of that.
So you could sort of see it here, right? It's 2 pi r. It's theta
so it's
r.
it's a feature of plane geometry. When I said plane, not because it's ordinary, but because it is on a flat two-dimensional surface called the plane, the plane. This is on the plane.
Anyway, I think we're getting close to the end. So we should look at the answer.
On the plane, the arc length S, measure around the arc, is equal to the measure of the central angle in radians.
Yes, I know, Seth. We've done it like 10 times. We're done.
Times the radius of the circle.
All this stuff. I mean, come on, we're done. Okay, so the answer is a third. So let's see how they do it. Oh, we have to answer. Oh my God, look at this. We have to actually put it in. 1/3. Okay, check. Okay. Okay, now let's see. See how we answered this question. Okay, that's good that they're modest. They didn't say, well, let's check the answer to the question. That's how we did it. That's right, because everybody does it different ways. So it's only a three-step problem, three-step question. We're interested in the fraction arc length divided by circumference, right? Exactly. And then they have the formula, which, if it's on this sheet, you really should know it for the SAT. The arc length of an arc of an A, the length of an arc subtended by angle theta is r theta. Therefore, you just plug it in. Arc length is theta. They give you the central angle, 2 pi over 3, divided by 2 pi. They don't show you how to do the complex fraction, which many people forget. So we need to show how to do a complex fraction. If you have A over B divided by C over D, it's called a complex fraction. This is equal to A over B times the reciprocal of the denominator. They don't really show it here, but they should.
So what I don't like about that, what they wrote there is ambiguous. 2 over 3 over 2.
Absolutely. They need a big... Notice I did it. Notice my intuition as I made a big bar.
Indeed, yeah.
Of course, yeah. If you go back to when I did it, go back to the video, you'll see I made sure to make it look more like this. You have to.
Yeah, could it be,
Yeah, that is
2
ambiguous. Yeah.
Divided by...
Yeah, we know it's ambiguous. Okay.
3 halves? Or is it...
I know, right.
Or is it 2/3?
Right, yeah.
Divided by 3.
That's right. It's completely ambiguous.
Yeah, difference.
Yeah. Okay. So today's Throwback Thursday. On Throwback Thursday, we go back to tests, SAT tests, from before 2016, where the tests had more of a, had more of an IQ feel to them, more reasoning from this book of 20 years ago. So let's do that, and then we can end with our introductions. Okay, so Throwback Thursday. Ready, Seth?
Yeah.
This is our Throwback Thursday question. And I think it's geometry. Now, back then, they had 5 answers, and you got penalized if you got the question wrong. If you guessed, they would penalize you. At least they did that when we took it in the 70s. I'm not sure if they did that in the later years, like 20 years ago. Okay, so here we go, and I will annotate through. I'll annotate through Zoom. Okay, here we go. Triangles ABC and ABD share side AB. Oh, I hate geometry when they don't give you the picture.
So draw the picture.
Yeah, I know, but I'm going to read it first. Triangle ABC has area Q and triangle ABD has area R. If AD is longer than AC and BD is longer than BC, which of the following could be true? Right, so this uses that thing about the triangle inequality. There's different triangle inequality.
I don't think so.
Anyway, let me see. Okay, ABC. So let's just draw a regular vanilla triangle. A, B, C, and then ABD. So we make D a little funky. We put it there. It's isosceles, but for now, okay. Now, triangle ABC is area Q, and triangle ABD is area R. Now, if AD is longer than AC, how about if we totally cheat and make this D and make this C? Okay, now we cheated, right? If AD is longer than AC and BD is longer than BC, okay, well, that's good. I got that right. Which of the following could be true? Wow. The area of R is greater than Q. R equals Q. Wow. R is less than Q. Well, it's probably not. Wait, R is less than Q. See, the problem... Well, actually, the problem here is I know what the person answered. I never actually looked at the answer. Well, okay, fine. The area of a triangle we know is 1/2 the base times the height. But this perhaps is being too detailed. You have to be really smart to do this. Do you know how to do it, Seth?
Well, look at my picture.
What did you do? You made a D, that red thing.
Let's do a circle. Let's draw a circle.
Okay.
Let's draw a circle around A. That's not okay. Let's draw a circle. Let's see. Could we move the circle when we move it? I don't think so.
If you do it in Sideboard to count. No, you're not on Sideboard.
Okay, I
Okay.
can't do that. Okay. Uh,
You could draw the circle and erase it and redraw it.
yeah. What I want to do is draw a circle around A of radius. Let's call this. Let's say call this R. I don't like it. R. A. Let's call it A. Let's call it X.
Fine.
X. X is the length of AD.
Fine.
And let's imagine many possible triangles that share line AB and whose length AD equals X.
Okay.
That's so the constant is that AD equals X. Therefore, point D lies on a circle. Like that. See that, everybody?
Not yet.
D could be on a circle.
Yeah. Okay.
Radius is X.
Right.
So there could be lots of D's.
Yeah.
And for each one, like this D here, for each of those D's, you have a different triangle. So you have triangles that are, so remember, the length of AD is X. It could be a triangle that's all squishy down, very, very skinny, very, very small area.
Right.
Or there could be a triangle where the area is a lot bigger. Or the original triangle, the area is maybe a little bit is maybe even bigger. So but then the other triangle whose area is R, imagine that being fixed. So you could vary one of the triangles to make it, you could make the original triangle really small, like and then vary the other triangle to be very, very squishy, have a very, very little area. You could have it have a very big area. That's chosen to be bigger than the area of the R triangle of the other triangle.
Okay.
And so all possibilities, including equality, are possible. So the answer is 1, 2, and 3.
Wow. If AD is longer than AC and BC. Wow. I mean, that's what the person who answered it said.
Yeah.
Let's go to the answer book. So let's see. Math, section 2.
Yeah.
Number 22. The answer is E. Congratulations, Seth. Wow. Wow. So this definitely has a whole different feel from the modern test, doesn't it? Yeah. This is not something you would normally learn in school. It's not a straight application of what you would learn in school. You would have to do what Seth did, which is employ drawing, I guess, auxiliary lines or auxiliary circle, extra stuff to help you see what.
Well, a clue to it is the following: that what's fixed about the two triangles, what mathematicians will say invariant, is the length of AB. They both share the same one side, one length of side is shared by the two triangles, AB.
Right.
And then they talk about the area.
Yeah.
Well, what they teach in school is that what they teach in school relevant to a triangle where the length of one side is fixed.
Yeah.
What is the area? The area is that fixed length multiplied by not the length of the side, but the height of the other vertex off of the side whose length is fixed. area is 1/2 of the product of the fixed side's length and the height of the other vertex, not the length of an edge to the other vertex. So since it's the height, you have to worry. Well, this is not the length. This is about the lengths of two sides of the other two sides that are on the common vertex A, and that's being compared. But what does that to do with the height? So what does the length of a side say? So the vision this puts in my mind is this we have a fixed base of the triangle, right?
Right.
And we have we have one side of one vertex of the triangle, vertex A, right? And then we have a range of other sides that have the same length, right?
Right.
All of these little blue lines have the same length, but they have varying heights over the red line. The ends of them have varying heights. The height of the end of the blue line is proportional to the sine of the angle, right?
Right.
And so the angle varies, the height varies.
Okay, Seth. How about if we? I mean, you did it from the point of view of being someone with. Oh, we should introduce ourselves because otherwise you don't know where we're coming from, right? Because when you talk to someone, you should know where they're coming from. Seth has a PhD in mathematics from MIT. He's been a professor at University of Albany for a lot of years. He's retired. He's professor emeritus. I have a PhD in mechanical engineering, so I view things from a practical, just get it done type of method. And we are here to hopefully show you how to approach studying for the Math SAT. We strongly encourage you to go to Khan Academy and take either course, the digital and non-digital course, and talk to your guidance counselor as to which test you're going to be taking. So we come from different methods of doing it. Now, not that many people, it's possible that there are going to be a few people who don't come from, no one's going to come into the SAT with your background, with a PhD in math and teaching computer science, and also doing shapes of stuff. Seth did shapes of stuff, his PhD, sort of graph theory type stuff. So he really knows this stuff cold. Let's say you don't. Maybe one approach to this is more of a brute force, and draw some pictures and play with it. Now I was just looking at it. The picture I drew, which is completely consistent with what they said, clearly R is less than Q, right? It's pretty obvious that this is totally valid picture I drew, and R is less than Q. So this is good. And I guess you could think a little bit about it. If you could make a picture that R is greater than Q, then if it's less than Q and there's a possible greater than Q, you would think, because things are sort of, I'm going to use a higher level word, continuous, where things go smoothly, that this would also be true, if this is true. So maybe one approach that I probably would have done, because I don't have the same experience as Seth, is I would have tried to find an example where I could draw this where R is actually greater than Q. So should I try to do that, or is it going to take me?
I did it already.
Where is it, Seth?
It's this one. Yeah, right here.
It's the red one?
Let's call it.
Make it green.
Green.
Yeah, make it green.
Yeah, this one. D. Oh, come on. D. This is the D.
Right.
Yeah. Yeah, there.
Yeah, where's the
This is this triangle in green. Oops, sorry.
Oh. Okay, let me do it in
Yeah.
black. Let me do it in black. Wait, you're talking about this triangle.
I'm doing it. It's green. It's green and black. Yeah.
A little slivery
And
triangle.
call it Q. Call it,
Yeah,
black,
I did.
green or black Q.
Black
It's a
Q.
little skin. I said little squinty, little squishy,
Okay, but
squishy, skinny triangle.
Let's do devil's advocate here. Okay, fine. So
It's
A
the area is obviously
B
the green Q area could be made really, really, really tiny
yeah, A
by
D.
making D like very close to the extended line off of AB.
Wait. But BD doesn't look longer than BC, but we could change that. BD,
Yeah.
we could change. We could put B
Yeah,
here.
yeah.
Can't we put B here?
Yeah.
So that
Okay.
BD,
What's not constant? Of course, with that, and they told you. I didn't say it was constant. What's unconstrained is the length of BD. They said the length of. They said the length of. AD is longer than AC, right? AD is longer than AC. Uh-oh.
if AD,
We have two things going on.
if AD. Now, what about the really funky green triangle? Here, we'll put it in very thin black, just so that.
I think we made a mistake here.
Wait. This is the. How about red? Red medium. How about this one? We go to there. Go to B. This really, really weird looking triangle. Okay. That one there. Now let's see. Let's see. Wait. If AD is longer than AC, yes, it is. And BD, no, BD is not longer than BC. BD is shorter than BC.
Mm.
So we have yet to show where R is greater than Q.
Okay, this is where I made a boo-boo.
No, but the answer according to the SAT people is E. But let's say you're not a genius like Seth. Although actually, genius is, I don't know, it's not the genius. Seth just works really hard.
So we have two triangles, corresponding edges. Corresponding edges. The triangles are not similar, but of corresponding edges, one pair of corresponding edges are equal length.
Yeah.
And the other two pairs are respectively the length in one triangle is longer than the length of the other triangle.
Right.
Right?
AD is longer than AC and BD. Yeah. Both lengths are longer than the other lengths, but they're not corresponding, right? There's no. Yeah. You have two triangles. One side is the same, and in triangle Q, the two sides are bigger than the two sides in triangle R.
Yeah. Uh-huh.
So we got to find a triangle using brute force where R is greater than Q, where the smaller triangle has a greater area than the one with, say, the larger triangle. Is that?
Yeah. This is really. This is where I got carried away because I went too fast. You have to watch out in SATs about getting carried away with an idea that you get before you finish reading the whole problem.
But Seth, you were lucky that you got the same answer they got.
I'm not sure about this.
Look, the book's probably not wrong.
Well,
let me double check. This is section 2 of the math. 22E. Yeah. 22E, yeah. Wait a second. Now the problem here. This is what happens when you. This is.
Oh, I
Can
think.
I clear the drawing?
Yeah.
Okay. We got to go to a nice cool color because we're
Uh-oh.
both getting a little upset here.
Yeah, I'm getting all upset today. Yeah.
But when you struggle, when you do a problem and you don't really
Uh-oh.
understand it, you have a responsibility to yourself to sit here and torture yourself like we're going to do. We got to
Okay.
find a triangle where r is greater than q.
Yeah.
So
Oh,
we
come
have
on.
we have a triangle here. We have A
Oh.
and B. And now we're saying that there's a big triangle, generally big triangle here, because AC. No, A. Wait. AD.
Okay.
AD is longer than AC. Okay, so let's just do it again. AC, right? So these sides. Let's compare the orange sides to the blue sides, right? And BD, and then we compare the blue sides, right? And this one's bigger than this one. So you want to get the essence of the problem.
Okay. Now, we have a problem. Well, rather, this is now I'm going to actually have to bring up show everybody my education in mathematics.
Oh God. Everyone may want to go
I
with
want
this
you to uh let's see. I want to share my let's undo the screen sharing.
Oh, I don't think this is going well. Okay.
And I want to share my screen.
Okay, God knows what people are going to see when I say. Okay, stop share. There we go. Go ahead, Seth.
Okay, now I'm going to do a screen share and show you something from the web. Do you see? Do we see that?
Yeah, the old Heron's formula.
Yeah.
It's a cool way of calculating the area of any triangle, no matter what it is. Right triangle, left triangle, no left triangle, right triangle, obtuse triangle.
Right. So what is it? It is the let's see. I'm going to do. Can I do annotation on this? Sure. Yeah, I could do annotation.
Yeah, you should.
Yeah, I'm going to do annotation on Herod's thing. So it gives a formula for the area of a triangle in terms of these quantities S, called the semi-perimeter, and the lengths of the three sides.
Right.
So S is 1/2 of the sum of the lengths.
Right.
So let's see what this comes out to be. The square root, and what are they? So we have 1/2 of A plus B plus C.
Yep.
And then that's multiplied by 1/2 of S minus A. Let's see, S minus A is minus A plus B plus C, right?
Right.
And the other term is 1/2 of A minus B plus C.
Right.
And the last term is 1/2 of A plus B minus C.
Remember, everyone, just say a prayer. Your prayer's been answered. You don't have to
Okay,
know all
now,
this for the SAT now.
If say we increase both B and C, then this term goes up.
Right.
Here, B plus C also goes up.
Right.
Now, if you increase B and C, this term well, could go up or go down
Yeah.
depending on the relative how much A and B and C go up and down.
Right.
But however much this goes up, if this goes up by X, this goes down by X.
Right.
Right? So if you have, A plus X times A minus X, right? A plus X and A minus X. How does that compare with A? How does that compare with A squared? When X of A, how does that compare with A squared? Well, it compares with A squared via, well, this is A squared minus X squared, right?
Right.
So if X goes up, this goes down. And if X goes down, this goes up, right?
Right.
So according to Herod's formula, we cannot conclude from Herod's formula that the area, say, goes up always when both B and C go up. Huh.
Wow.
So that doesn't give us too much. That gives us a little bit of insight. So I think we ought to follow Joel's approach and seek examples.
Yeah.
Where when B and C go up, the area goes down.
So it's going to probably be a weird triangle.
Yeah.
Because the default triangle, the normal vanilla triangle, looks not like that. So we have to be really creative. We have to go obtuse. We have to go obtuse crazy. Maybe we look for an acute triangle. Maybe we have to look for each type.
Yeah.
Acute, obtuse, right?
Yeah.
Oh God. I guess we have a responsibility to ourselves and to everyone watching. Although no, I'm sure very few people are here at this point to try to do this. So should we?
Okay. Let's stop the share.
Okay, let's start. Oh, is this it? Yeah. I'm gonna switch to Zypeboard. At least I'm gonna go Zypeboard.
Well, we could do it another else. Let's think about it another way. Here we go. Suppose we start out with, two triangles. The two triangles, say, being equal area, right?
Right. Good idea.
And now let us see what happens if we increase the lengths of one of the edges.
Wait. So you're saying, so if the triangles, you mean like literally like this, where we literally go this way, and we go.
Yeah.
Wait. D, C, and we go like this.
Yeah. Okay. And now if we increase the length of AD.
Right.
What happens?
Well, and BD gets big. Obviously, there's default is that it gets bigger, but we have to come up with a way of increasing AB and BD.
Yeah.
But have.
No, my thought is that, if we could say move from. Okay, I think let's try a different approach. Get rid of that. Please get rid of that.
Wait. Hold on.
Get rid of it. I have another thought.
Wait one second. We if we go back, I think we confused R and Q.
No.
No, R is
Go.
greater. Wait, stop. Did I misread? ABD. ABD is R, so 1 is obvious. 3 is the one we have to work on.
Yeah.
When we did it, I mislabeled R and Q.
Okay.
Yeah, but it doesn't matter. It doesn't matter.
It doesn't. Yeah,
right?
it doesn't
So
matter.
this is
Yeah.
obvious. Okay, this is obvious. We have to show this. Need to show this.
That can't happen.
Example. Okay?
Yeah.
We need to show example where R is less than Q. I'm sorry for everyone who actually survived this far, but I think I mislabeled R and Q. But in the end, it really doesn't matter. Okay. So we have to show an example where this is the triangle. We'll call this the triangle with bigger sides. How can a triangle with bigger sides have an area that's smaller than a triangle with smaller sides?
Okay. Now, again, more imagination is needed here.
Imagination.
I'm going to use a different way of drawing it.
Okay.
I will at the bottom draw line. Draw line AB. Right, then I'm going to draw one triangle. Oops, sorry. I want to make them with straight lines. I'm going to draw one triangle up here. Okay. And now I'm going to draw the other triangle, not below it, but on top of it. Right?
Right.
And then we could move all of these lines around. Okay? You know, so the idea is let's using the notation, the letters, that the green triangle, let's say, is the D triangle.
Right.
And the blue triangle is the triangle vertex of C.
Right.
So rather than seeing them on opposite sides, look at them on both on the same side.
Right. That's a good idea.
Right? That makes it a lot easier to see the issue. The issue, right. See, the issue is the area of the triangle is the is the length of the base
times its height.
Times the height, right? Okay. So,
and I'm going to put it in, but this is the height, okay, everybody? That's the height. Those are the heights. I'm going to erase those.
Yeah.
And the base is the same. That's a really good way of thinking about it. Yeah. So that's invariant. The AB is invariant, and the heights are more easier to see.
Yeah.
Right. So now, BD. Oh, BD and BC. So these sides are to be compared, right?
Yeah.
And these sides are to be compared.
Yeah.
Right. Yeah. So you can have some really flat triangle, can't you?
Yeah.
You could make D go all the way out here. Just looking for weird cases, right?
Yeah.
The height is very tiny. Right? Now, here, BD, let's concentrate. Maybe we're getting somewhere. BD is longer than, BD can be really long. BD can be way out here, but very, very small height. Right?
Yeah.
My God, BD can be over in England, and this height is minimal. Oh, it's an obtuse triangle, so the height goes like this. This height is tiny, but BD can be hugely greater than BC.
Sure.
Now, what about what happens with when AD? Oh, and AD. Oh, this is B. This is B. This is BD, right? This is BD. Yeah, right. Yeah. And then BD no, and then right, and then AD, which is also this thing, goes off to England. It's
Yeah.
really, really high, really long, but its height is very tiny.
Yeah.
Very tiny, like minimal. And the AB stays the same, and the area is just based on its height. So that's it. That's how it works. Wow, so that was really good. And when you do geometry, this is the old reflexive property coming in. You know, when you do geometric proofs, you have this reflexive property, the same line shared. That was really insightful. Some people in geometry may have had questions like this. I always found them annoying, where you have different types of triangles, like typically a triangle here.
Yes, it's a subtle question.
Here, a triangle here.
And so let's do a what do you call it? After a play is over.
Yeah, analysis.
When you go back in the locker room and you discuss it, what went wrong, how could where could have been played better, what were good moves? What do you call that?
Well, right now we're going to review the approaches that we suggest.
No, I mean in sports.
Yeah, analysis. You do analysis.
What analysis?
Analysis. Yeah, analysis. Yeah.
Yeah, the analysis of the play. Well, when I realized that I stupidly skipped over one of the assumptions of the problem. Then I thought of Heron's formula and said, wait a minute. According to Heron's formula, maybe that when the lengths of corresponding sides increase, the area increases. So I looked at Heron's formula, expecting to get an insight from that, and it turned out no, it's because the half is the semi-perimeter is used in subtracting.
Forget the Heron's formula approach.
Yeah. The Heron's formula approach puts in minus signs.
Yeah, forget the Heron's formula approach. It's not appropriate for
the Heron's formula, I thought I could demonstrate that it's monotonic using Heron's formula. But then when I looked at the details of Heron's formula and did the calculation, I realized, nope, it doesn't.
Yeah.
So it led me to rethink the first guess.
Right.
And now, when Joel started fussing with the two triangles that were congruent, one on the top and one on the bottom, I thought this is really. It's hard to think of two triangles, one on top and one on the bottom. It's much easier to think of the two triangles whose area you're comparing are actually on the same side of the common base.
Right. So big approach. If you are comparing areas of triangles, try to get a common base. Okay? That's a big takeaway. If you're ever asked to compare triangles or parallelograms or any shape, parallelograms are based on site, get a common base. And that's really the secret key to the problem.
Okay, so now that we draw the common base, Joel realized that you could make long, skinny triangles. Long, skinny triangles with tiny area, and make them area much smaller than the area of a much smaller triangle. A triangle with whose edges are a lot shorter, bigger areas. I could have a triangle with long, long non-horizontal edges and small area, and shorter non-horizontal edges, a bigger area.
Yeah, for example,
and then compare it with and then compare that with the thing that one would think of first, which is the triangle with the longer edges has longer area. So let's draw a picture of a case where the D triangle has much bigger area. The case where the D triangle has much bigger area
Well, we did
would
that
be.
already. We did that.
Let's draw that. There's the D triangle.
Seth, but we did it already in the general
No. I want to do it. Let's do it this way. Here's our D triangle. Let's put it up here.
Make it an acute triangle. Don't make it obtuse. That's all.
Like that.
Yeah, just make it an acute triangle, a friendly triangle. I hate to diss the
there's D.
obtuse triangle, but
So this triangle has these long edges.
Yeah. You don't have to. Seth, we're done.
Yeah.
We're done.
Okay.
So I just want to show everyone where this big idea of sharing common bases, comparing triangles, comes up in your common geometry textbooks. You may have seen pages like this in your textbook where they give you different triangles. See those things, and then they ask you find the ratio of these silly shapes, these different triangles that are inside each other. The key is you don't actually calculate the actual area of those things. You calculate the ratio by looking at common bases. These problems may have looked familiar. See those things where they give you these strange-looking triangles inside each other? See that? So this is where this concept comes up in your geometry class, where you probably have seen it. But that's the key to this problem. I mean, that's the key to drawing examples to the problem, which frankly seems to be the most probably the way most. I know Seth hates when I say that, but come on, it's probably the way most people would have done. But who knows? Most people taking the SAT aren't lucky enough to have a PhD in math. But even still, Seth had the PhD in math, and he still did it the wrong way because he misread it. But he still got.
Well, now we're listing all the things that happen and the experience of math. So call to mind of something of experience of math. People who are into math, who like math and are good at math and recognize as math people, they always make mistakes.
Oh yeah.
The whole thing, part of the fun and one of the elements of experience in math, and you ask any mathematician how much they make mistakes. If they are a mathematician who's been into research, actually done some mathematical research, is a research attitude, they will reply, mistakes occur in my mind all the time.
That's right.
That's different from what you ask a kid who's no good at math. Ask a kid, if you're good at math, do you ever make mistakes? And the kid will say, oh, I can't be good at math because I make mistakes all the time.
Right.
But you ask a mathematician, do you make mistakes a lot? I say, oh, yeah, I make mistakes every day.
Right. Yeah.
Okay, so the first step in getting over dislike of math is to accept and appreciate that mistakes are what math is about.
Right, mistakes are the way you really learn.
Math is interesting because thoughts that are mistakes will turn out to be surprises.
Right.
It is a surprise when you make a mistake and then discover that it was a mistake.
Right. Yeah, that's why if anyone, we're going to have to go back to the YouTube in a few days. They actually tell us how many people got this far. It would be a miracle if anyone did. Anyway, if anyone did, congratulations, you got to go because we're done. Okay, everyone, I hope you enjoyed Throwback Thursday. You will never see a question like this on the modern SAT, thankfully for most people. But hopefully you got something out of it. Remember, when you compare areas, get a common base. Okay, everyone, have a great day.
Maybe the SAT they'll give in the year 2070 will have questions like this.
I don't know. But if you ever have to compare areas in the triangles, get that common base, because that's where the question's heading. 98% chance that's where the question's heading. Okay, everyone, I think we really, really are done. Oh, yeah, like us, dislike us, give us comments, and if you have any SAT math questions, please email them to us at satmathquestionoftheday@gmail.com, and we hope to see you tomorrow. And we took a break for a while, but we are back. Bye-bye, everyone.